Batteries taught us how to store energy, but they are not the final answer to a world trying to move beyond fossil fuels. Some energy demands are too large, too continuous, or too heavy for batteries alone. That's where fuel cells and hydrogen enter the picture. Not as futuristic ideas, but as chemical systems that can generate electricity cleanly, continuously, and efficiently. This is the Learning Studio, where chemistry is explained as the driver of energy transitions, not just technology trends. And after understanding how batteries store and release energy, the next logical step is to explore how chemistry can produce electricity directly from fuels without burning them. Most people think hydrogen energy is about explosions or rockets, but in reality, fuel cells are controlled electrochemical devices. For example, in a hydrogen fuel cell, hydrogen gas reacts with oxygen from the air to produce electricity, heat, and water. There is no combustion, no smoke, and no carbon emissions, just chemistry converting fuel into usable energy through electron flow. At the molecular level, fuel cells operate on redox reactions similar to batteries, but with a crucial difference. Instead of storing reactants inside the device, fuel cells continuously receive fuel from the outside. Hydrogen molecules are split into protons and electrons. The electrons travel through an external circuit, generating electricity, while protons move through an electrolyte and recombine with oxygen to form water. As long as fuel is supplied, electricity flows. The scientific foundation of fuel cells goes back to William Grove, who demonstrated that electricity could be generated from chemical reactions without combustion. Later, Wilhelm Ostwald emphasized that fuel cells represent a fundamentally more efficient way to convert chemical energy into electrical energy compared to heat engines. Their insights showed that chemistry could outperform combustion on purely scientific grounds. Hydrogen plays a central role because it is the simplest and cleanest fuel. When used in fuel cells, its only byproduct is water. However, hydrogen is not an energy source, it is an energy carrier. Producing hydrogen requires energy, and the chemistry of how it is made determines whether it is truly clean. Electrolysis powered by renewable electricity produces green hydrogen, while fossil-based methods introduce carbon emissions. The challenge is chemical, not conceptual. Fuel cells offer advantages where batteries struggle. They can be refueled quickly, provide continuous power, and scale to heavy transport, industry, and grid-level applications. This makes them attractive for buses, trucks, ships, backup power systems, and long-duration energy storage, areas critical for decarbonizing the global economy. Yet fuel cells also reveal chemistry's constraints. Catalysts must be efficient and durable. Materials must resist corrosion. Hydrogen must be stored and transported safely. Each of these challenges is rooted in chemical stability, reaction kinetics, and materials design, showing again that the energy transition is fundamentally a chemistry problem. And once we understand how fuel cells and hydrogen can generate clean electricity, the next question naturally follows. If chemistry can convert fuels into power, then how can it convert sunlight directly into usable energy without fuels at all? That question takes us directly into the next episode, where we explore solar chemistry and how light can be turned into electricity and fuels.